Sample exam 5, problem number 27. Let x and y have a joint density function of f of x is equal to 2 times e to the minus x times e to the minus y for x greater than 0 and y greater than or equal to x less than infinity. What is the marginal density of x where non-zero? Problem number 27 of sample exam 5, we're asked to find the marginal distribution of x. And we're given the joint distribution. This is the joint density right here. And so to find the marginal of x, we integrate out y. And y goes from x to infinity. So then you take the antiderivative of that, plug in the limits, we get 2 times e to the minus 2x, where x is between 0 and infinity. Problem number 28. Observations y1 through yn are assumed to come from a model with expected value of yi equal to theta plus 2 times the natural log of xi, where theta is the unknown parameter and the xi, the x1 through xn, are given constant. What is the least squares estimate of theta? Number 28, we're asked to find the least squares estimate of theta. And what we do is we take the sum over all our data, which is yi, and subtract the expected value of the line, square it, and then we minimize it for all values of theta. And we do that with the derivative. So we take the derivative with respect to theta, and it's 2 times this, we minus 1. And then chain rule says we got to take the derivative of inside respect to theta, and we just get minus 1. So set it equal to 0. So this minus, we can take it to the other side and we still get 0. We can take this 2 to the other side and we still get 0. So then the sum of the yi, and there's no index here, so that just there's n of those. And then here it's the sum of the log of the xi, still equal to 0. Take this over to the side and divide by n, and we get n is equal to the sum of the yi minus 2 times the sum of the log of xi divided by n. Number 29, suppose x has the density function f of x is equal to 1 over theta. X is between 0 and theta and 0 otherwise. If one observation of x is taken, what are the probabilities of alpha and beta of type 1 and type 2 errors respectively, and testing the null hypothesis that theta is equal to 1 against the alternative hypothesis that theta is equal to 2 if the null is rejected for x greater than 0.92. Now number 29, they provide the rejection region of x greater than or equal to 0.92, and they want us to find the alpha and beta, the probability of a type 1 error and the type 2 error. So type 1 error, we assume that the null hypothesis is true, which is theta equal to 1. So we integrate here from 0.92 to 1, and it's this 0.08 is alpha. Now beta is the probability that we don't reject the null hypothesis when we should. So that's the type 2 error. So we're integrating less than 0.92, so it's 0 to 0.92, and the alternative hypothesis is theta is equal to 2, and then we integrate that, we get this, plug in the limits, we get 0.46 is the probability of the type 2 error. Number 30. Suppose there are n plus 1 slips of paper numbered 1 through n, and where each piece of paper has 1 through n, and then another piece of paper has an n on it. So there's 2 n's. One slip of paper is randomly selected, its number recorded and then replaced. This is done a total of n independent times. What is the probability that the numbers recorded in any order are 1 through n? Now, number 30, there's n plus 1 slips of paper, all with different numbers except 2 of them have the value of n. And we're asked to find the probability that when we draw them, we get, with replacement, which is pretty important here, what's the probability that we draw exactly, one slip with a 1, a 2, a 3, all the way to n. So now let's look at one possible ordering. Okay, this isn't the answer, this is one possible ordering. That we draw a 1 first, then a 2, and then etc. all the way up to n. Well, this is the probability. There's only one slip out of the n plus 1 that has a 1. There's only one that has a 2, etc. And there's 2 that has an n plus 1. So this is the probability of one particular order. Now, if you think about it, if we would have switched the 1 and the 2 here, the probability still would have been the same. As a matter of fact, we can permutate any of those. We could mix them all up and this ends up being the same probability. So each specific ordering has the same probability. So really, the probability that we draw 1, 2 through n on any order is the probability of the specific event, because they're all the same, times the number of ways you can mix them up. And the number of ways you can mix in numbers is n factorial. So this is the answer. Problem number 31. Let x1 through x17 be a random sample from a continuous uniform distribution on the interval 0 to 5. Let t denote the smallest observation in the sample. What is the cumulative distribution function of f of t for t in the interval 0 to 5? So number 31, it has to find the cumulative distribution function for t, where t is the first order statistic, or the minimum. And here we're provided that x is a uniform 0 to 5, yep. And f of x you can find as x over 5. So the cumulative distribution function of x, not t. So now to find the density of t, and again, this is something you're just going to have to grapple with until you get it. And once the light bulb goes on, then it becomes very easy to find densities of order statistics. So this is the order density of the first order statistic, or the minimum here. Now to find the cumulative distribution function, we go from 0 to t of this density here. Now when you take the antiderivative, you get this. Plug in our limits, we get this. And then I like to write the 1 first, which is 1 minus t divided by 5, all raised to the 17th power. Number 32. Let x1 through x100 be a random sample from the uniform distribution with mean mu and variance sigma squared. If phi is the cumulative distribution function of the standard normal distribution, then what is the probability that the sum from 1 to 100 of the xi is less than or equal to a times mu is closest to? So number 32 is we're asked to find the probability that the sum of the xi is less than a times mu. And here, that, and x is a uniform distribution. So to find the density of this sum would not be fun. Not be fun at all. And so we're going to have to use the central limit theorem to find this probability. And it says that the sum, assuming the second moment is finite, approaches a normal distribution. And that in the second moment finite is important for example, a Cauchy distribution. Anyway, that's another topic. So let's find the mean of these. So you take the mean in. The mean of one xi is mu, but we're summing from 1 to 100, so it's 100 times mu. And then the same way, the variance of this xi is 100 times sigma squared, which is the variance. And they tell us the mean of one is mu, and the variance of one of those is sigma squared. So here, if we subtract the mean and divide it by the standard deviation of both sides, so we subtract the mean, divide by the standard deviation, which is the square root of this, it's z. So z is less than this. And then by definition, the probability of being less than a value when we're in the standard normal is this notation here. So that's our answer. Number 33. A box contains two coins. One has probability 1/2 of heads, while the other has unknown probability p, where p is between 0 and 1 of heads. A coin is selected at random and flipped. It is then replaced in the box, and the entire procedure is repeated another time. If two heads are observed, what is the value of the maximum likelihood estimator of p? Okay, so problem 33, we're going to let xi be the outcome of the ith roll, and it takes on a value of 1 or 0, and that corresponds to a head or a tail. And if we look at the specific coins, so we have coin 1. If the flip of coin 1 is a binomial with 1 in 1 and parameter 1/2, and coin 2, we don't know what the probability of a head is, so it's just p. So now let's look at one flip. Now we're going to do this twice, but let's just look at the first flip. You grab a coin, you flip it, and then you put it back. Randomly pick another coin, grab it, flip it. But let's look at the probability of one flip. So x1 equal to 1. So we're trying to find the probability that it's a head. Now, if we introduce the coins, so the probability that we get a head and we grab coin 1 plus, that we have grabbed coin 2, we're summing over all possible values here. It doesn't change it. But this allows us to write it as a conditional. And then we do that because once we know what coin we grabbed, then the probability of a head can be determined quite easily. So this sum is this written out. And now the probability that we grab coin 1 is 1/2. And if we know we grabbed coin 1 or selected coin 1, the probability of a head is 1/2. And then this probably grabbed coin 2 is 1/2. The probability of a head, given that we're using coin 2, is just p. And then this can be simplified a little bit to this. Okay, so that's one flip. But we're interested in the probability that both flips are 1. But they're independent, so we can write them independently. And the probability of each event is the same. So the probability of 1 is this, probability of x2 1 is this, so it's really just squared. And then if you were to take the derivative of this to find, in quotes, the maximum, you would get that p is equal to -1/2, which doesn't make sense. And then if you were to take the second derivative of that, you'd get 1/2, which sort of shows that that is a minimum for this probability. But if we graph this, that's a quadratic function with the minimum at -1/2, and it touches it. But p, we're only interested from 0 to 1. And so how do we maximize this function? Well, we let p equal 1 because that's the maximum that it can be. So the answer is p is equal to 1. Number 34. Suppose x1 through x12 are independent random variables, each normally distributed with mean 0 and variance sigma squared. The most powerful critical region of size 0.025 for testing the null hypothesis that theta or sigma squared is 10 against the alternative that sigma squared is 5 is given by so here we're asked to find the most powerful critical region, and here's the joint density of our data x1 through x12, and we're given that it's normally distributed. So then it's just a product of all those individuals. So this, raised to the 12th, sigma raised 1 over sigma raised to the 12th, e to the minus the sum of xi squared divided by 2 sigma squared. And the mean is 0. So that's why there's no extra components there. And the most powerful critical region is this. We set up the densities like this. And the null hypothesis is that sigma is 10. Now notice when we take the ratio of this drops out. And then this is, for the null, this is 1 over 10. So that kind of goes to the denominator. And the denominator, which sigma squared is 5, goes to the numerator. So note, that it's 12, but I divide by 2 because really those are the variances, and that's the standard deviation there. So we have to take the square root of that, and then we plug in 10 and 5, for the variance, and we get this. Now we take that to the other side, and then we raise this one up so that becomes a positive exponent. And then we factor out the sum of the xi squareds to get this. And then we take the natural log of both sides and then divide by that, and we get the rejection region is that the sum of the xi squareds less than k is the rejection region. So now to find the value of k, we're given that alpha is 0.05. So we need to find the probability that this sum is less than k is equal to 0.025. Now, under the null hypothesis, the true sigma squared is 10. So if we divide both sides by 10, this piece becomes a chi-squared with 12 degrees of freedom. So then the probability that chi-squared is less than some number is equal to 0.025. That implies that this piece right here is 4.4. So it equals to k over 10. So then you solve for k and you get k is 44. So the rejection region is we reject if the sum of the xi squared is less than 44.